Alright, so in this video, I'm going to talk about different forms of the ideal gas law that you have seen so far. So far you have seen different forms. I got an email from one of you, really good question the person was asking. So I would like to explain what is happening. Like all of them are the same, but how they are related all to each other. So some of the forms of the ideal gas law that you have seen so far is PV equal to RT. This is probably the most common form of the equation that I was using so far. Here, P is the pressure, V is the specific volume, R is the gas constant, and T is the temperature. Okay, now the unit of P is kPa, the unit of V is meter cube per kilogram because that is the specific volume. The unit of R here is kilojoule per kilogram Kelvin, and the unit of T is in Kelvin. All right. So here V is specific volume. Now, if I start from one side, I will end up with the same unit that I have on the left hand side. For example, here on the right hand side, so let's say the unit on the right hand side is basically kilojoule per kilogram Kelvin multiplied by Kelvin. So this is the unit of R on the right hand side, and this is the unit of T on the right hand side, and I will end up with kilojoule per kilogram. So this is the unit that I have on the right hand side. Now let's see if on the left hand side I have the same unit or not. Unit on the left hand side says my pressure is in kPa, my specific volume is in meter cube per kilogram. So what I'm going to do, I'm going to expand this kPa based on kilonewton per meter squared, because that is the definition of Pascal, multiplied by the same thing here, meter cube per kilogram. Okay, so this cancels two of the m's that I have here, so I still have one m, and then I will have kilonewton meter over kilogram. And you know that Newton meter is joule basically, so I will have kilojoule per kilogram. So you see that the units are the same. So this is the unit that I have on the left hand side, and this is the unit that I have on the right hand. So the point is, here this V should be a specific volume. Okay. Now another form of the ideal gas law that you have seen is PV. So this one was lowercase and this is uppercase V. PV equal to N RUT. Okay, now these two equations have something in common, and in both of these two equations, I mean this one and this one, P is the same, T is also the same, so pressure, temperature. Here my V was a specific volume. Here this V is just volume, okay, meaning that the unit is meter cube. Here the unit of a specific volume is meter cube per kilogram, okay, but here my V is meter cube. Now here I have N on the right hand side, so this N is the number of moles. This RU is different from this R. This was the gas constant, and for each gas we have a unique R value. So the R value that we have for nitrogen is different from the R value that we have for oxygen. Here, this is the universal gas constant, and it's a fixed number. Okay, so this RU is universal gas constant, and no matter what gas you are working with, this number is the same, and that is 8.314 kilojoule per kilomole Kelvin. So the denominator is kilojoule per kilomole Kelvin. So this is the unit in the denominator. All right. Now, here is the point. Here, this R was in kilojoule per kilogram Kelvin. Here, this RU is kilojoule per kilomole Kelvin. And the reason that they chose a kilomole for the unit is because they wanted to have a number which is applicable to all gases. They wanted to have a universal value. So because the gas density or the gas specific volume is different, they cannot really have RU based on kilojoule per kilogram Kelvin. That doesn't work. RU, in fact, should be per kilomole, which is the amount of gas, so it's applicable to all gases. Now, let's do the units. Let's start with the unit on the right-hand side. So, unit on the right-hand side says, I have number of moles. So, let's say kilomole is the unit for the number of moles. RU, here is the unit, kilojoule per kilomole Kelvin. And then I have the temperature of, the unit for temperature is Kelvin. So let's say this Kelvin cancels this one, this kilomole cancels this kilomole, and I will have kJ on the right hand side. Okay, now let's see what is the unit on the left hand side. Okay, I'm working on this equation. So pressure is kPa, but this time instead of meter cube per kilogram, I just have meter cube because this is volume, okay, and that is meter cube. So I expand kPa into kilonewton per meter squared. That is the definition of Pascal. And then my meter cube stays. So I have 2 m's canceling 2 of these m's. So I will end up with 1 m here. And I will have kilonewton meter. So you know that Newton meter is joule. So that means I will have kilojoule on the left hand side. So here we see that the unit we have on the right hand side is the same as the unit that we have on the left hand side. So that is the difference between this equation and this equation. This equation is per kilogram on both sides. I ended up with kilojoule per kilogram. Kilojoule per kilogram. But here, because this V is just the volume, not the specific volume, then my unit is just kilojoule. This is not kilojoule per kilogram. So because of that, this is a specific volume. Okay, so the other form of equation that you may have seen, I think back in Thermo 1, we did it at least once. So we had PV, again, capital V, meaning this is volume, equal to M, lowercase m, R, T. Okay, so this is the equation that we had back in Thermo 1. At least we used it once. Okay, these two equations are kind of similar to each other because on the right hand side of both of these two equations, I have R. So here I have R, here I have R. There is no RU. And I have T. So the only difference is here I also have M, which is mass. Okay, and that's why I changed the lowercase v to uppercase v. So this is volume. All right. So this is my volume once again. So you know that the unit on the left hand side is kilojoule. We did it on the previous equation. So if I do the unit on the right hand side really quick, so M is mass and the unit is kilogram. R is the same R that I had here. So this R is the same R that I had here. That means unit wise on the right hand side. So unit on the right hand side becomes kilogram multiplied by kilojoule per kilogram Kelvin multiplied by Kelvin. So this kilogram cancels this one, this Kelvin cancels this one, and I end up with kilojoule. Right? And I know that the left hand side PV also has the unit of kilojoule. Okay, so these are some of the forms of the equation, the ideal gas law equations that you have seen. But in fact, all of them are the same. It really depends if you're working with volume or specific volume. Okay, so this is RU here. And yeah, so these two we is capital, and that is volume. So let me clarify that here V is volume, and that is meter cube. Okay, the other equation or the other confusion that you may have is about or is between R and RU. Okay, so let me talk about these two. So you know that we had an equation R of M or of our mixture, the gas constant of the mixture is equal to RU over apparent molar mass. Okay, so that means we have two different forms of R. So do not be confused with this subscript M. You can kind of ignore that because this gas constant is the universal gas constant over the molar mass. Okay, so the unit of Rm here is simply kilojoule per kilogram Kelvin. That's the unit of R. Again, do not be confused with subscript M. That M only says this is the gas constant for the mixture, but it doesn't really change the nature of the R value or the R property. RU unit is kilojoule per kilomole Kelvin. All right, and MM is just the mass, molar mass, right? So kilogram per kilomole. So if I work on the right hand side, I mean the unit here on the right hand side, this kilomole cancels this one, and I will have kilojoule per kilogram Kelvin. So this kilogram and this Kelvin, that is the unit that I will have, which is pretty much this one here. And by the way, getting back into the ideal gas laws, like these three equations, all of them obviously have a z term on the right hand side, but because I was discussing about the ideal gas, I didn't really include that. But you can also consider a z on the right hand side. For instance, you can assume that here there is a z, here there is a z, here there is a z. Okay, if we are talking about an ideal gas, that z is equal to 1. So we don't really bother to show that. But you can still use pretty much the same equation whenever you are dealing with a real gas. And in that particular case, your z is not equal to 1. You have to obtain the z value from figure A15. This is what we have done in a couple of problems. So I hope that this video clarifies like the different forms of the equations that we have. All of them are kind of the same. This is my sincere recommendation. If you work with units, you will not be confused. So make sure that you use units in your calculation, in your equations, and also check the homogeneity of the unit on both sides of the equation. If you do that, you should be good, hopefully.